All right, so we're going to continue the utility evaluation for the global measures. And I think last time we were at the global measure about, yeah, we're using the logistic regression to the propensity score. Right? So the propensity score, if you remember, is a way to check, the effects of the intervention. Like that's the generic how propensity score is being used. But then when we're doing it in the utility perspective, what we're doing is we're thinking about the intervention, the synthetic, and then we're trying to use, you can do logistic regression, you can do other model, like in the sense that we stack the two data sets together, right? We create this one extra column, and then trying to use the existing, like either the unsynthesized values, but more importantly, the synthesized values, and then check if we are able to do a good prediction in terms of whether observation should belong to the synthetic and whether the observation should be belong to the original. So we looked at a way, the steps of how to do this, and then I gave you the demo of doing it using R. And at the end of the day, we're looking at this measure in a sense that, so U stands for utility, P stands for propensity score. We're looking at the predicted probability of each observation belonging to the synthetic data. And then we're looking at, so that's PI hat out of the model that you do. And then you look at the difference between that and 1/2 because we stack the two data sets together. So, in theory, it should be 1/2. Half of the data set, half of the data points should belong to the original, the other half should belong to the synthetic. So we're looking at the difference, we squared it, and then take the mean. Okay, so this UP, the closer it is to 0, the higher the utility, because that means it's going to be more challenging for the model to differentiate the synthetic data and the original data. However, if you have a vastly different distribution characteristics between the synthetic and the original, then that will be the case that many of the PI hat, this value, will either be 1, close to 1 or close to 0. Okay, because close to 1 meaning that that observation will be very likely being classified into the synthetic data set. Closer to 0 meaning that it will be very unlikely to be classified as the synthetic data. So that will give you a overall UP to be close to 1/4. So like 0 to 1/4 will be the range of UP. Okay, and then so the closer it is to 1/4, the lower the utility, and that's how we're using this. Okay? So the demo that we did using R, and we're using the synthetic C sample where I used a simple linear regression synthesis model to synthesize log income given log expenditure. So we talked about how we can do that. And this is how you synthesize the data. We saved it to be synthetic_1. And then you merge two data sets and then add the S variable. So you have this one extra column. S is 0 if it's original, it's 1 if it's synthetic. And so we do all that. So the logistic regression that I use is this. And we use the GLM function in R, and don't forget that you should do family equals to binomial if you want to do logistic regression. And I'm including both explanatory variables in this case. And don't forget also that when so the predict function in R will be able to give you this beta 0 or B0 plus B1 times X1 and B2 times X2. That is what the predict function will give you. So it's not the probability per se, but it's, the logit. Okay, so you have to use this transformation in equation 3 to come back to get the PI hat. Okay, so this one, this exp pret over 1 plus ex pret is exactly doing what's on the right-hand side. And that's what we're trying to return. So we get the props, and the props is the one that we're evaluating the UP. So at the end of the day, we will have, in this case, UP is really small in the sense that it's near 0. The logistic regression model cannot really distinguish between the two data sets, so indicating a high level of utility. Okay. All right, so that's the first one that we trying to cover last time. So we're going to continue from last time. The second one is cluster analysis measure. So cluster analysis itself is a commonly used technique. The gist of it is trying to cluster records with similar characteristics together in the same group. And then the records clustered in different groups going to share less similarity. Okay, so we're trying to cluster observations with similar characteristics. The thing is, once you have observations grouped in one group, then certain characteristics, for example, if it's a numerical variable, you want to estimate the mean and the standard deviation. So you're able to use all of the observations that you have clustered in that group to have improved estimate. Okay, so the thing is, similar records, they're clustered together based on the cluster analysis, and they're going to share information. Okay, it will be especially beneficial if you have clusters with small sample sizes, and that is the case that so like in a sense that you have a few more, ideally if you can, some more records to be used to estimate your mean or standard deviation or any kind of group specific characteristics. Okay, so the method itself, if you remember, at the end of the Bayesian class, we did a case study about the scores, like the true or false scores. If you remember, like people like we're trying to figure out if there are two groups back then. One is the random guessing group. The other group is the knowledgeable group. What we were talking about back then is that we have, I think, about 20 people's scores of like 40 true or false questions. Yeah, 40 true or false questions. We have their scores. So we have like a group of observations, I think around 20 or like below or a little bit above 20. So we're thinking that maybe they're the random guessing group because I mean, by random chance, you might have 50% chance of getting it correct. Okay. And then we also see a little group of observations or cluster of observations like at the higher end, like maybe they score on average 30 or 35 or even close to 40. So that will be the case that cluster analysis can be used, and that was the methodology that I covered back then, in a sense that we don't know the group of each observation belongs to, okay, but we know there exists two groups. Okay, so we're trying to use cluster analysis in the Bayesian method in particular. Is trying to assume that each observation belongs to one of the class, but we don't know what it is, right? So remember we wrote the JAX code and then trying to do all that. So just to refresh your memory, we did something along the lines in the past. But this cluster analysis, as you will see, and I think many of you have implemented, is not really a Bayesian method. I mean, there is Bayesian flavor of it. You can do a Bayesian version of it. But just as the propensity score, we're using logistic regression from the GLM function, right? We're doing a frequency classical inference for calculating those utility measures. But those methods themselves, I mean, you have Bayesian version of them. You can always do a Bayesian version if you want. But for simplicity and also for computation, I think consideration, we're just going to do what we have with the classical inference. Okay, but I mean, the general idea is it's the same. Okay? You have clusters. You want to cluster observations with similar characteristics together. So there are many algorithms out there, and in short, each algorithm has its own understanding of what constitutes a cluster, like what goes into, like what you are using to form the cluster, and also how to efficiently find the clusters. And also, you can be really flexible. You can use all of the attributes or variables to form your cluster, or you use a subset of it. Okay, so depends. I mean, some very complex data set, you can use all kinds of information, and so this is another like thing you have to consider when you are trying to use this cluster analysis as your utility measure. Okay. In class, we do simple demo, and the key here again is trying to differentiate. They discriminate using it as a utility measure. We're trying to see if the measure can discriminate between the two groups: the synthetic group, which is the synthetic data, and then the original group, which is the origin data. So what we do, very similarly to before, we first of all merge the two data sets. Okay, and so if we have m by p for both of the data sets, the merged data set, we stack them together. It's going to be 2m by p. We're also going to add an additional variable here, the same as before, 0 to be from the original and 1 to be from the synthetic. So we know that for the logistic regression earlier, for the propensity score, we have to have this additional variable binary so we can do a logistic regression to do the prediction. Here is because now we know, I mean, we always need to have an indicator here to know the truth. Okay, we want to know the truth in a sense that we want to know where does each observation come from. It's either from the original or the synthetic. Okay, so we're gonna keep in mind with that. Did I miss a slide? Maybe I missed a slide somewhere about the, yeah, I definitely missed it. You know what I'm talking about, like what the measure itself is. I think it's the UC somewhere from the paper, right? You know what I'm talking about? Let me pause here real quick. I might move that slightly like earlier just because I mean I'm getting into talking about how to do it now, but I think it's important to look at the end goal, what we're trying to do. All right, so okay, so once we have that stacked data set with a new column, we're going to perform a cluster analysis on the merged data set, and we can do a fixed number of groups in a sense that, or fixed number of clusters using capital G. So once we run the cluster analysis, we'll be able to know how many observations falls into each group. Okay, so with each group, small g, once we do the cluster analysis, we're going to find the number of records clustered in this group. So I'm using n subscript small g to indicate the number of records in total, both from the synthetic and from the original. And then also I'm going to record NGS. This is the number of synthetic records fall into that group. Okay, so well, you know, we never define NGO, but that will be like the number of original data sets falls into that. Okay, but that would just be NG minus NGS equals to NGO. But you know what I mean? We only need one of this in order to compute the final measure. Then the following measure is in equation 4. So let's look at it carefully first. 1 over G, and also all of this sum. So you know that like once you take the sum and then divide it by G, that's getting a weighted average. Okay, and the weighting is done this way. So if you look at the right-hand side, what is weighting doing? So we have this WG, which is weight. We're going to talk about that in a minute. So this ratio, this is the number of observations from the synthetic data in group G, right, on the top, divided by the number of observations combined from the original and the synthetic. So this is the ratio of the synthetic over all of them. Okay, and then we're minusing the C, and as it turns out, C is going to be 1 over 2 again, because in our data set, we have half of the merged data set, I should say, we have half of them from the original and half of them from the synthetic. Okay. So this is saying we're looking at the difference from the cluster analysis ratio of the synthetic over the all observations in each group. Okay. We're looking at the difference between that and 1 over 2, because if the two data sets are really similar to each other, that ratio should be close to 1/2. Okay. And then we take the square. And the key here, as you know, the formulation has this WG. So W stands for weight, okay, stands for weight. And it's the weight assigned to cluster G, okay? So I wrote it here available from the clustering algorithm, but I think it really depends on what kind of algorithm you're using. I'm going to show you a way that using a particular hierarchical clustering algorithm, you might not get WG directly, but you can still approximate it in a way that you want to weight. So the weighting here, the reason why we want to do the weighting is because, well, sometimes you will have a larger cluster, sometimes you're going to have a smaller cluster. Okay, so later you're going to see that in the demo, we're going to have 5 clusters in total, but only 2 of them are heavily occupied because the remaining 3 have very little observations in them. So we want to give like higher weight for those clusters with more observations and lower weights of clusters with fewer observations. So the WG, I'm later just simply gonna do it as a weighted average, like as a weight from the total observations, I mean the observations in group G over the total observations. So keep in mind, we have a WG here, and the reason is because we want to do the weighted average instead of a simple arithmetic average. Okay, makes sense? Yeah, and as you read through the paper, you know that like C, they use C. And in the slides and all of the instructions, I'm trying to use 1 over 2 because in our evaluation now that we are just stacking them together. Okay? We have the same dimension of the original and the synthetic. But more generically, if you have different dimension of the original and the synthetic, then that C will just change accordingly. Okay, but for us, we have the same, so it's half and half, so C is half. All right, so so we talked about this. If all of the observations are, if the cluster analysis cannot really distinguish between the two data sets, the synthetic and the original, then the percent, like, it's going to be a lot of groups going to have this close to half, right? This ratio close to half. So the whole thing about UC going to be close to 0. Okay? So that is when you have a high utility. And low level of similarity between the two different data sets going to result in this UC to be larger. Not close to 0. And in the sense that if you have a large value of UC, this ratio could be close to 0 or 1. And then when you're taking the difference between that with 1/2 and then take the square, take the weight, then UC will be further away from 0. Okay? So the gist is UC close to 0, high utility. UC further away from 0, but positive, always positive. It's going to be indicating low level of utility. I think intuitively overall this makes sense. So to do it in action, I came up with something, but I'm sure people might have other algorithms to do this. So once I introduce what I did, we can hear from you. This is, again, we are using the C sample. It's synthetic data with log expenditure unsynthesized and then log income synthesized. Okay, so now you know this is partial synthesis. Okay? And so step 1, do the merge and then add the additional variable. Step 2 is to perform the cluster analysis. What I'm using is the HC, hierarchical cluster. Okay, so that's what it stands for. It's a function in R. I forgot which package, but anyway, so yeah, so it's a readily available package. Can do that to you for you. And what we're doing is we are applying this function and the merge data, because we're clustering only not based on the S column. Okay, so that's the key. So the first one, I think, is the first column is the log expenditure, I think, in the merge data. And then the second column is the log income. Okay, we only want to do clustering based on those variables, not the additional S, because the additional S is only there for us later to do the counting. Okay, so make sure that you don't specify like that S, because that shouldn't be part of the clustering. Okay. And I think there are different methods you can use. I chose average just as a default, but if you want, you can explore that H plus function a little bit more. And this is overall run pretty quickly. I think they do a hierarchical clustering for you. The way that I figure out how to fix the number of groups is, so you know those clustering algorithms, they're usually trying to like grow trees. That's what they say. Like they start with all observations. They start with everything together, but then they slowly branching out. Okay. So what they do, my understanding, is they can grow. So whatever there's clusters, once we have done, so this is the object that we save the output of, right? We save the output of the H plus method of our data set into this. So you can grow the tree into many, like very detailed level. But in order to like fix the number of groups, if you want, you can do the cut tree method, in a sense that if I pre-specify the number of groups I want for this method, I can set it to be 5, for example, and then I cut the tree that I grew by pruning it in a way that I only want to have 5 groups in the end. Okay, so that's how you can. So in the sense that whatever is lower than the level 5, further more detail, they're just going to be aggregated back to the upper level, like higher level. So at the end of the day, I'm only going to have 5 groups. I think that's what it means. So once we do that, I save this to be cluster cut. And then what I do is, because at the end of the day, remember we want G and G, that's the number of observations into each group, right? We also want NGS. We want the number of observations into each, the number of synthetic observations into each group. So what we really need is we want to column of the cluster assignment, right, for each observation, right? We also want a column of the S variable, that's the indicator variable of whether it belongs to the original data set, which is going to be 0, and whether it belongs to the synthetic data set, which is going to be 1. So we want to do a table, pretty much, a contingency table of these two columns. So each row is an observation. So that's why I c-bind those two columns and then create a data frame, because later I can use the table method in a sense that I can, in the end, create a desired contingency table here. So there might be other ways. Mine might not be the most efficient. It took me some time to figure out what it's doing. I mean, the cluster algorithm itself and also how to use it. And my understanding, so I rename the two columns just because later we can see it on the table what is for what. So if you read this table, this A67 is the number of observations from the original data set, because that's column 0, right? And being clustered into group 1, right? And then this AA3 is the number of synthetic observations being clustered to group 1. And you will have this two. Oh, okay. So I guess in my output, there are 3 heavily used clusters, whereas 4 and 5 are not so much utilized. I think it was yesterday I saw TEDs. I think TED, you had 2 clusters mostly used, right? Yeah, but it depends on the algorithm, depends on how we prune the tree, whether you set 5 or, yeah, it's all like open-ended. This is more like a demonstration. Okay. So what we have here, all of the 2 columns, so this column, I should say, it's this column is the NGS, right? It's the count of observations, from the synthetic data into each group. Okay, so we need this column later to compute our statistic in the end. We also need what? We need all of the row sums, because we need the sum of the 2 at each row to get our NG, okay? Because that's the number of observations from either source, original or synthetic, in each group. Okay. So that's why on the next slide you saw that probably that I create my NGS to be the first column from that. Okay, my NG is the row sums of that table. So I get, so this is like 5 elements, and then the weight here, as you see, I'm doing a simple weight that the weight of each group is the number of observations falling into that group divided by the total number of observations. So this is an empirical weight. So it's the percentage of records clustered in group G. Okay. So now we have all of the pieces, because what we want UC to be 1 over G, right? Sum from G from 1 to capital G, and then we're going to have WG, and then what is it? NGS over NG minus 1 over 2 to the power of 2. So that was the measure that we talked about earlier. So we need all of the pieces. Now we have WG, we have NGS, we have NG, and our C is 1/2. So with all of the pieces, we're ready to compute that UC measure. So the demo that I did in the end have a really close to 0, I think, UC utility measure as well. Okay? So that means the cluster analysis algorithms cluster roughly equal numbers of observations from the 2 sources into the same group. Okay, that also means, I mean, in addition, this means that cluster algorithm cannot really distinguish between the 2 groups. So that indicates high level utility because they're so similar to each other. All right, so I'm gonna pause here. Maybe you can share with your neighbor what you did. Maybe you did something similar to what I did, especially using the H plus algorithm, or maybe you use something else. But at the end of the day, we need to have the framework that we are able to do. Yeah, we need to have the framework that we're able to get WG, NGS, and NG. And so in the end, we're able to compute this UC. Okay, but You might use different algorithm, you might use a different package, so that's totally up to you. So let's just have a quick small group discussion of what we did and what you did individually. And if you have something to share, we'll have the time for you to share what you have done. If it's different from what I did. Right, so let's hear from some of you if you have anything to share. I mean, I have the stop sharing here. Right, I have the GitHub page here. So anybody did anything different from the clustering algorithm that I did and that you wanted to like share with the class?
I don't know if this is worthy of sharing, but Henrik and I were just talking. So I did, and I imagine this would hold true over like any specific clustering algorithm.
Can
but if you
yours here,
go into lab 3, page 10.
it's lab 3.
So the reading proposed a number of different cluster values. Or like so I was just like, all right, I'll try them over like kind of a whole grid of clusters. So if you go up to the plot above.
Oh, I see.
And like one thing you see is that like the cluster score gets worse and worse the more clusters you do. And Henrik and I were talking, and I would imagine that's because as you get closer to having like a true row of the data set and its synthetic version, like they're less and less similar. So it's like as you get more granular in your cluster, they look less alike. And on one hand, that seems like a good thing because you're protecting identity that way. But then also, is your data not like representative of the true underlying data? It seems like paradoxical to me.
Yeah, I see. So can you like tell us a little bit more about this graph? So I understood in a way that the x-axis is like you're increasing the number of clusters, G, right? And then the y is the UC measure that you calculated. So what are each dot here?
So I think I did a bunch of synthetic samples, so it wasn't just one. I see.
So
I think I before knowing like why m equals 20 or any of those, I just took 20 because I knew that was a number that had been thrown around. So just to show that it like wasn't just that synthetic, like they're all kind of at least centered somewhere.
Right. So each dot, I guess, say like here at when G equals to 100, I get each dot represent the UC measure from one synthetic data out of like say 20 that you did.
Yeah.
Okay. So this is a good plot because we can now see variability across different synthetic data sets. So we know that like later, I mean, for today's material, you know that we are generating 20 synthetic data sets from the same model from like independent MCMC iterations from the MCMC chain. But still, you're gonna have variability. And then this is a good way to visualize at least, that we're able to see the variability of the UC measure, which is the utility cluster analysis utility measure across the synthetic data. But this plot has more to that. So as Isaac was saying, the x-axis here is, going from, I guess, very small 5 groups to 200 groups. And it's not like continuous, we're just looking at particular points, like 100 or 75 and then 50 and then up to 100 and then also some smaller choices. And we see a general trend from here that as the number of clusters increases, the UC measure deteriorates, right? Deteriorates because it keeps climbing in a sense that if we use too many clusters for the cluster analysis algorithm, our cluster analysis utility measure, we're going to see different outcomes. If you chose 200 in the first place, you might determine that, well, the utility using cluster methods might not be that good. But if you started off with 5 or even smaller, the one that I had was super small, right? Close to 0, I think 0.006 or something. Yeah, so this is, so the number of clusters is sensitive in a sense that the number you chose will have, from 5, you have 0.25-ish, and then to 200, you have close to 0.4. Okay, so you have vastly different different utility outcome, and then you might make different decisions based on that. So I think Isaac was trying to share with us, like say, if you have more clusters. So imagine how many data points do we have? We have close to 1,000 in the original, right? Like 994, I think. So double that, close to 2,000. That's the total number of observations that we have once we stack up the two data sets, right? So we're doing clustering algorithm for 2,000 data points. So there is, cluster analysis itself, the research field itself, I think it's actively trying to figure out how many or what is the optimal number of clusters to use. So apparently this is something that we get into it. And here as well, to some degree, that if you have 200, on average, what each cluster will only have, on average will have about 10 observations, right? Based on that. And based on what I had, so let me stop sharing here really quick and then bring this back, because you saw that. So this is something we need to keep in mind when we use this measure, because the one that I had, I remember I only had 5 clusters, but really only 2 are heavily populated, right? Where was it? When I did the table. So that's why I wanted to look at this table briefly, at least, to get a sense of what we're getting. So this table, so this is one synthetic data set, not multiple. And we looked at G equals to 5, and then we looked at, when I chose U equals to 5, you have so many. Most of them are in cluster 1, right? And some in cluster 2 and 3, and then very not used 4 and 5. So if I look at like this kind of results, I might even cut my G to be 4 or 3, because the thing is, the more clusters that you have, unless the algorithm is flexible enough that it wouldn't use that many clusters if it doesn't need to be. Otherwise, I think it will be like a little bit challenging if you have too many clusters. And as we saw earlier, like when we have 2 clusters based on Isaac's result, that we might have a deteriorating utility. And maybe we need more. We don't know. That will be an interesting, actually, research topic. If that will be something that you like, any of you would like to pursue a little bit more in this course. But clearly, using the cluster analysis measure, the number of clusters will be something important to keep in mind. Okay. Cool. Anything else? Let me come back to the. Kevin, did you say something earlier as well?
Oh yeah, I just said I use the k-means.
Okay. So that's another very commonly used. So is it?
It should be global analysis.
All right. So is it here?
Mm-hmm.
Okay. Mm-hmm. Yeah. So can you tell us a little bit?
Yeah. I just click around the groups and I just picked 10 as like.
Fair enough.
What that was, because they're all about the same, like between like 5, 10, 15, 20. And so I just went through all the groups, and I didn't do it very elegantly, but just kind of merged all to calculate the UC score, and then I got about 0.15. It looks like a little bit down more.
Here?
Yeah.
Okay.
Yeah. So 0.15. And I wasn't really sure, like in the paper, it didn't really explain if that was like the similar score of like a reasonable, if it was, I think.
Oh, right, yeah, because it's either close to 0 or not close to 0. Like it's not like the UP propensity score that we know it's going to be between 0 and 1/4, right?
Yeah.
So this one, yeah. So do you know much about like k-means? And do you want to share something about it?
Yeah, just like a general thing. It kind of like, I think the number of groups, like the number of means it tries to find, and then it like centers those around like the weighted average of like that mean location to all the points there. And it just keeps like iterating and iterating until the algorithm like converges when it doesn't change any of the locations, and eventually just have a bunch of different size groups. So
so then the number of groups that will be the k, right? Like say you started off. So one thing I noticed, I don't know how, because like say the cluster analysis that I was trying to use both the unsynthesized log expenditure, right? And then the synthesized or unsynthesized, depends on the original or synthetic, but I'm trying to use 2 variables to do the cluster analysis. And you might have other, I mean, like in this case, I think what Kevin did is the k-means is only being applied to the income. Yeah, so which, I mean, we might have different ideas and you might have your own ideas, especially later when you do your project. But this is something like we need to keep in mind, like how many, just like, yeah, clustering, like we said earlier, in this case, in the CE sample, we just have 2. We only have 2 variables, but you can decide if you want to use both of them, right? To do the clustering. That might provide a bit more information because you might be able to capture the relationship between these 2. If you're only using 2, using one of them, then you're only looking at the univariate case. Okay, so that would be another thing I think to keep in mind. You can, yeah. One other thing quickly, like, did you get the chance to do also the what is it? The weight here?
Oh, that's another thing I was gonna write, is that I didn't know with that package, I guess, the k-means, how to find the weight from.
Yeah. So I wonder, like, say, to be honest, like, because I thought the weight going to be automatically from the package as well, but when I did the H plus, I don't think they return you a weight anyway. So for me, I tried to approximate the weight based on
The size.
Yeah, the size of the cluster. So that might be something you can hard code here
I'd
if you want. Okay, yeah. Okay. Anybody else? Okay. All right. Okay.
Oh, yeah. I was just wondering because I kind of did the same thing as on Isaac,
Yeah.
but then my results are kind of opposite, where you got more clusters and you just
Oh, I see. Do you have it like
called CE sample PDF or something. CE sample assignment PDF.
oh, here? Okay. All right. Let me. So which page? Oh, is it down? I guess.
Wait, isn't that? Oh yeah.
Is it this document?
Yeah.
Oh, it's here. Okay.
And I think down there a little bit. Yeah. And I just added the number of clusters
Oh, I
to
see. Yeah. Oh, I see.
almost like to 25, 50, 100, 200.
Yeah.
And the utility just even increases.
Let's see. Yeah. So it's an interesting trend. Okay. So I guess Maggie wrote a function. The input is the number of groups that you have, right? So you have 3, 5, 10, 15, and 20. So we started off small. I mean, highest utility, right? Because the UC is really low, like lower than, I mean, lowest actually. And then when you bump up to 5, it's a little bit larger. Bump up to 10, then they start to decrease. So it's hard to tell the trend now. And also, I mean, what Isaac's showing, I'm not too sure like what the cluster mag algorithm was used, but clearly, I mean, this is another demonstration, I mean, from Maggie here, that I think the number of clusters is sensitive, I mean, the choice of that. So that, I think it's probably one of the drawbacks that they talk about in the paper. Or if not, I mean, clearly we are seeing that. So that would be something like, I think good to keep in mind, that because this is one extra thing you have to tune. Okay. For the propensity score, well, to be fair, the propensity score, I mean, it really depends on what kind of model you're using to predict the probability, right? Like I used the logistic regression using both of the, both the log income and the log expenditure. You might even want to do interaction terms, and so you can have like this. So that's another variable in the sense that you might play with that, tune that to see how that will affect your final utility. Okay? For cluster analysis, as we can see here, the number of groups is probably a key player here as well. Okay. All right, cool. So let me finish up this lecture by covering the last global utility, which we know is the empirical CDF. So we all know CDF, and if we know a particular density function, we're able to express the CDF. But then when you're working with actual samples, I mean, you don't even know what the distribution it follows, so it's really hard to get the analytic solution, but you're able to do an empirical CDF. In a sense, I think it's pretty much just like you sort the data set, right? Like from, I guess, the smallest to the largest, and then you're able to like get a density plus CDF in a way that you sort it based on the orders and all that. And then the empirical CDF is sort of doing that. And then you can also imagine that if two distributions are very similar to each other, then the empirical CDF will be very similar to each other as well. So again, we're trying to use this commonly used technique, empirical CDF, and use it as a utility measure because we're trying to figure out if this measure will be able to discriminate between the two data sets. Okay, so it's very similar to what we did with the cluster analysis and the propensity score. So what we did, what we can do to do this empirical CDF measure, we still, first of all, stack them together, but we now don't really need the extra, column about whether one observation is from, do we need to merge? Oh, we do, okay. Yeah, now I remember. Okay, so it's a little bit more complicated than it sounds. The empirical CDF, so let me walk you through this. Okay, so the first step is merge them. That's all fine. The second step, so there are readily available R packages to estimate the empirical CDF for you. So you can do that. We're going to show you what to do. But the thing is, the procedure works. Has multiple caveats here. So first of all, we should estimate the empirical CDF of the original data. Okay, so that's just M by P. Okay, so that's the thing that you did. And I denoted, might not be the best notation, but like ECDFO. And you also estimate the CDF distribution of the synthetic. So we denote that by ECDFS. And then, so what I mean by using appropriate functions and methods, so you might be able to find something on, or I have found that one that might be that could work, or you might have other things. So remember, first step we still merge them, but then the second step we're doing the estimation separately, right? We estimate on the original, we estimate on the synthetic, because we want to get empirical distributions from each of them separately. Okay, so they are separate. We're trying to see if we can discriminate between them. So then what comes into play in the third step is that for each record, we have in the Birch data set, we have a 2n number of records in total, right? What you do is actually, for each record, it's either from the original or the synthetic. What we do is you estimate the percentile under the CDF of the original, okay? And you also estimate the percentile under the empirical CDF from the synthetic. So notice that when you estimate the empirical CDF on the original data set, which has M by P, so you just get, you get the empirical CDF, you just imagine it is there. But you can use any other record, even in the data set or outside the data, to estimate the percentile. Okay, so you can think of the empirical CDF as, like a function. And typically, it's a CDF, so it's not that drawing. It should be decreasing. Something like that. Right? So let's just say if this is ECDFO, so that's the ECDF from the original, right? So what we want is for any record, some of them are in the original, some of them are not in the original, right? But for any record, we want to get the percentile if we place that record back to the empirical CDF of the original. Okay, and we do that for the empirical CDF of the synthetic as well. So what we're doing essentially for any record, let's just say for record I, okay, we look at its percentile in the empirical CDF of the original. We also look at the percentile of it in the empirical CDF of the synthetic. So if the two empirical CDF distributions are very similar, then any record that I put in, the percentile should be that off, right? They should still be close to each other. And if they are, if the two distributions are quite different, the empirical distributions are quite different, then any given record that I estimate its percentile on will be different. Okay, so again, we're trying to capture how big the difference is between the estimated percentile under the two different empirical CDFs. Okay? So again, the empirical CDFs, the closer they are, the higher the utility. But how can we produce a measure? Okay, you can always graph it and all that. But the paper is giving us an idea that you can estimate the CDF, empirical CDF separately. And then you can look at for any record in the original or in the synthetic, you estimate its percentile under the two different empirical CDFs. Okay? And then we check one record, like record by record, to see how close they are. So that's why it's a little bit, I think, it might be a little bit confusing now. Oh, why do you estimate your empirical CDF on the two different data sets separately? But then when you're trying to estimate the percentile, you can use any record. So the reason is because we want to estimate the empirical CDF separately because that's representing what the distribution is like for the original and then for the synthetic. Okay? But then we still, like we do the first step, merge them by stacking them together because at the end of the day, I want to estimate the percentile of each record in the merged data set according to two different empirical CDF. Okay? And then I want to see how close they are. So this rationale, I think, is slightly different from the other two. I mean, especially from propensity score, right? Because, or the other two, because the first two, what we're doing is we stack them together and we use both of them, I mean, all of them together to do any kind of analysis and then look at the differences there. The empirical CDF itself, I mean, works differently. So we have to estimate it first separately. And then we stack up, I mean, the two data sets and then look at the utility in that way. So that's why when you're trying to use those functions, I mean, the functions in R, we have to be a little bit careful what they're estimating, right? So the paper proposed two measures. One of them, I mean, the first one is the maximum absolute difference between the empirical CDF. So we're looking at the percentiles, taking the absolute difference and then return the maximum, okay? The other one is the average. Not surprisingly, you take the difference, take the square, and then sum them up, divided by 2n, because that's how many observations you have. Okay? So the maximum give you like the worst case, how big the difference are, okay? How big the difference is for a worst case scenario, and then the average will give you a general, I mean, like a data set level sense of how big the differences are. So these are, I mean, mathematical expressions. Once we get into our code, it will be yeah, more straightforward. So again, for both of them, if you have high level utility, then your UM and UA, so UM is the maximum, UA is the average, both of them should be low. Okay? If you have low utility, or I should say low level similarity between the two data sets, then you're going to have high values of UM and UA indicating low level of utility. Okay? So that's the logic. All right, so let me show you what you can do. Again, using the C sample, what I did is I generate one synthetic data. I merged the two data sets by not like adding the one extra column for the S, because for this case, we don't need it. So in R, you can use this, so it's in stats package, and I'm sure you have installed it already because you use it for other purposes, like even if you don't notice that. The ECDF is a function, you can use it directly. So the way that I'm using it is I'm trying to, yeah, so I use ECDF, and then I'm only using log income variable. So you see that the ECDF for the original, I'm using the original data looking at log income. Okay, so I save it, I mean, assign it to ECDF_ORIC. And then the other one is the synthetic data, the log income, and I save it into ECDF send. Okay, so these two later, we'll have to use this to estimate the percentile for each record in the merged data set. Okay, but those two lines correspond to the task that you have to estimate the ECDF separately. Okay. So I didn't figure out how to do empirical CDF of multivariable data. I don't know if anybody figured it out. So I think the paper was trying to explain that you can get the ECDF for not only just univariate, because I mean, I'm using log income. I'm only trying to do the empirical CDF of log income. So that's a univariate variable, right? But I think maybe I'm missing something in the R package, but I didn't figure out how to do that for, I mean, say if I want to use both log income and log expenditure to create my ECDF, I honestly don't know what to do. So I don't know if anybody got a chance or figure out what you can do. Feel free to speak up. The paper seems to be saying that you can do that for more than one variable. And I think that is probably a better way to do it, just because, I mean, even just earlier, I was pointing out to Kevin's write-up that the K-means that you used was only your income, right? And I thought it might be more, I mean, you want to use as much information as you can to do the clustering. So, I mean, I'm sure K-means were like accommodate multiple, because that's typically done. But for the ECDF, honestly, I didn't find out anything. But if you have figured out or like wanted to try that a little bit more, feel free. And I might just like keep exploring as well, because I think like doing it multivariate probably would make more sense. Right? So that's my question for you. If you ever have a chance to time to do that. Okay, so remember we saved the ECDF for the original and ECDF for the synthetic separately. And then what we do is you can do the percentile for the original from the original, I should say, percentile from the original and the percentile from the synthetic when you apply that into the merged data. Okay, so see how things are acting a little bit differently. So the two things that we save from here, they're functions. Okay, so even though, yeah, we use the ECDF function to be applied to the original data and then to be applied to the synthetic. So we save them into objects here, but those two objects apparently are functions. Okay, so that's why you are able to use them as function to evaluate the percentile of the new data. The new data meaning is the merged data. So that's something I think is pretty cool. I guess that's usually how people use this ECDF function in the first place. I'm not too familiar with that, but I think even though I couldn't figure out how to do it for multivariate, but at least for univariate, we can achieve what we want. Like we can estimate the ECDF first, and then we can return the estimated percentile from the original and from the synthetic for each record in the merged data. So that's a key. So I just follow what I did, and I think in the end I got something. Yeah, the maximum is 0.05. The mean actually is pretty low in a sense that, well, we take the square, so to be fair, I mean, it will be smaller even. But overall, I think, well, the paper never talked about how low is good enough, all that kind of stuff. So I think this is useful to some degree, but also, I mean, if you really want to like create some kind of a guideline, I think some kind of theory work is needed to indicate, well, what is a good threshold or what is a cutoff point and all that. But at least I think using this, we are able to produce those measures following their procedure. And let's see, yeah, also small, high level utility, and then that's the reference. We're mostly using that paper. Any comments before we go to the other section? Questions? Yeah, so if anybody like figured out how to do the multivariate data for the empirical CDF, let us know. I think that will be something handy. Yeah, because the formulation, I think they have on the paper is for, I think, dimension D. Okay, they have multiple, like multivariate. They can have like D attributes or D variables for each observation. Yeah, so I think in theory, I mean, the thing is you can always like manually do it if you want, but I think for us, we want to understand how the method works and then figure out the most efficient way to do it in R, like we can leverage what we have, I mean, public available in those packages. Okay.